Good evening, everybody. Welcome to Slooh, and welcome back to my Intro to Astro course. If you've been following along every week, you might have noticed last week that I took a hiatus and I had to cancel my show. And I'm very sorry about that. What happened was me and Michael Palucci, we were in Washington, D.C. at the NSF conference for the NSF grant that we have, which is really exciting. And unfortunately, because of Nor'easter Toby, a snowstorm that hit the northeast of the U.S. last week, we were delayed a day, and we didn't make it home. So I had to postpone the show until this week. So we are 1 week off from the schedule. But what's even better about this, that I didn't even realize, was that I totally went backwards on the syllabus. So this week was supposed to be about the dark universe, and now, if you'll notice, it is about the Big Bang, which I think is perfectly okay because I think it's cool that we'll end this course about the dark universe, leaving you all in the dark. Haha, I'm going to make that pun probably a lot next week, so I'm going to ask you to bear with me. But let's get right into it with the Big Bang. We're talking this week about the evolution of the universe, so all the way from the Big Bang to the present day and how we got here. If you're following along with me at slooh.com, I will be screen sharing so you can see some images that help illustrate what I'm talking about. And let's switch over to that right now. Here we go. So this is a really common image that we're looking at right here that describes the evolution of the universe, and you'll see it sometimes different colors, different formats. Sometimes you'll see it vertical as opposed to horizontal like this, but they all pretty much describe the same thing. Over on the left, where this big bright ball of light is the Big Bang, and if you look very closely, you can see that this sort of cone shape goes down into this teeny little point here, this little like nubbin or something on the top of this cone. That's the Big Bang. That's the Big Bang singularity. It starts from a point, and then what you're looking at is how quickly you notice that the universe grew. This is the expansion, the inflation period of the universe from the Big Bang, and it happens very rapidly. So if this is the whole 13.7, 13.8-ish billion years that the universe has been in existence since the Big Bang, this inflation happened very rapidly because you can see the rest of the time we stayed not, pretty much similar to the same size. But we'll talk about this in a little bit more detail. One of the fun statistics about this is that if the entire history of the universe, the whole 13.7 billion years, was shoved into a 24-hour period, the existence of modern humans like you and me would occupy just 0.00016 of a second. Oh my goodness. That is, we are so new into the lifetime of our universe. But so where did our universe start from? We talk about the Big Bang, and it's a theory that the universe started out being very small, very hot, and very dense in a almost actually infinite dense point or singularity. This is about, you'll hear 13.7, 13.8 for the age of the universe, and they're not interchangeable, but we certainly don't have a perfectly firm grasp on how old the universe is. So I usually say 13.8, but for example, the graphic I'm showing right now says 13.7. So, go with what you wish. But as soon as the Big Bang started expanding, it happened very quickly. It continued to do so, and the expansion rate has been increasing, actually, for the past 7 billion years or so. We are in an increasingly growing universe. The rate of expansion of the universe is increasing. So we are in an accelerating, expanding universe. Next week, when we talk about dark energy, we'll get a little bit more into that. But the Big Bang Theory actually predates the Hubble observations that show that the universe is expanding at an accelerating rate. Belgian priest, I'm not going to say this right, George Lemaitre, yeah, I don't know how to pronounce that, first presented the idea based on Einstein's theory of gravity, general relativity. This Belgian priest not only figured out that the universe should be expanding, but that if it was, it had to be smaller in the past. And this predates the Hubble observations, the famous Hubble observations that came to the Hubble constant, which actually turns out not to be a constant at all. Again, more things we'll talk about next week, but the idea that the universe is expanding did come before Hubble observed it. If the universe was smaller in the past, then everything was closer together. And if everything was closer together, then the whole universe must have been hotter, because when you shove a bunch of matter that has all this energy closer together, it'll heat up. It's like the law of thermodynamics. So at some point in the past, the universe started off incredibly small, hot, and dense. How big was this? Just about a few millimeters across, no more than the size of like an atom. An important distinction here, but one that's really tricky to get your mind around, is that the Big Bang was not an explosion in space, but an explosion of space. It was the appearance of space everywhere in the universe. Space-time did not exist before the Big Bang. And this is something we talked about a little bit last week with some of this higher dimensional thinking, as I called it. What happened before the Big Bang? And we don't know. All of the studies of the history of the universe up back to the Big Bang is as far as we can go. We don't know what happened pre-Big Bang. But we do know what happened post-Big Bang. So in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light. But this is totally cool. Einstein's theory of general relativity does say that light is the fastest traveling thing in the universe. Nothing can travel faster than light. But his theory doesn't say anything about the actual universe itself. So the space-time fabric of the universe was able to travel faster than the speed of light. This expansion is called the inflation period. So when we look at this graphic here, we have the Big Bang, we have some quantum fluctuations that I'm completely skipping, and we go into the inflationary period. This all happened within the first second after the Big Bang. In this first fraction of a second, the temperature of the universe was about 10 billion degrees Fahrenheit, and the universe was made up entirely of fundamental particles like neutrons, electrons, and protons. Within the first 3 minutes after the Big Bang, light chemical elements like deuterium, which is an isotope of hydrogen, so essentially hydrogen, and helium were created when the protons and neutrons collided. These are the elements that are abundant in the oldest stars. The free electrons that were floating around in these newly created atoms caused photons of light to scatter significantly so that light couldn't travel. Picture the early universe as like this opaque plasma or this fog of a bunch of fundamental particles, deuterium, helium, really light elements. And you know, when the sunlight comes through our atmosphere, if it hits droplets of water, such as a cloud, it scatters like fog. This is what is happening. And so this means that when you look all the way back far enough away from the Milky Way, back into the earliest universe, you hit this wall of light. You can't see back to the initial moment of the universe because this light was scattered so significantly that it didn't travel. Fast forward 380,000 years later, electrons are combining with the proton-neutron nuclei and forming these neutral atoms. This phase is called recombination. The absorption of the free electrons allowed light to travel around a less opaque universe. So once the free electrons were absorbed into the elements, into the proton-neutron nuclei, making these atoms, they were not in the way anymore, essentially. And now light could travel around the universe. So this relic light is called the afterglow of the Big Bang, and it's also known as the cosmic microwave background that we talked about a couple weeks ago. So when we look at this graphic here and we go through the inflationary period, before we get to the dark ages, which we're coming up to next, we have this afterglow light pattern. This is the CMB. So when we look all the way back through the universe, we see the cosmic microwave background. We see it everywhere, in every direction around the universe. That's called isotropic. Isotropic means the same in every direction. We see the CMB, and we look back and we hit this wall of the CMB where we can't go any further beyond it because light was not able to travel around. This is another graphic that displays what I'm talking about. And so I have two of them up here because they look a little different. One's a little more, not cartoonish, but maybe a little less busy and maybe a little bit easier to digest. So even though light is now traveling through space, the CMB, stars weren't formed yet. And the next period is called the period of darkness. It took until 400 million years later, after the Big Bang, for the next phase, which is called the age of reionization. But before we get there, the dark ages, this period of darkness, was because stars, even though we have the cosmic microwave background, this light that's permeating through all of space, we don't have bright stars. And so when we look back really far, we wouldn't see the bright stars and galaxies that we do here today. This graphic might display it better. We see all these bright stars and galaxies, but when we look back further, we don't. So fast forward 400 million years later, and we have the age of reionization. This is when the first stars were created. So now we're looking here on this graphic. Here. Clumps of gas started to collapse under their gravitational pressure to form the first stars. So we had these neutrons and protons and electrons that were in the very early expansion of the universe. Then the neutrons and protons formed these nuclei. They captured the free electrons. We started forming things like helium and deuterium. We had all this gas that started to coalesce, and then eventually the gas would pull in enough other gas, like streams, and it would increase its gravity, and then when it was under enough gravitational pressure from its own mass, it would collapse to form stars. And then eventually these stars would merge and start to swarm around one another and create the first galaxies. And so it's interesting, they actually say, astronomers think that the earliest galaxies were irregular shaped, not necessarily the spiral and elliptical structure that we see today. Those might have been formed more from mergers. So the original galaxies were probably somewhat of an elliptical shape maybe, but also irregular in that they were just stars that started to pull together under their gravitational force on one another. These collapses of stars and into eventually the first galaxies emitted very energetic ultraviolet light, which destroyed most of the neutral hydrogen gas that was from the recombination period. So now ultraviolet light is able to permeate through space, and we can see it. We have the development of galaxies, solar systems are starting to form, planets, etc. Gravity was essential in the formation of the universe as we know it today. Galaxies drew together to form groups and clusters. Stars started to outlive their lifetime, and supernova explosions happened, which seeded new star formation. And our solar system came about 9 billion years after the Big Bang. The universe was about 65% of its current size, which is why we say our sun is about halfway through its lifetime. It's about 4.5 billion years old. The heavy elements we see today, and indeed the ones that make up our planet and us, were created during these supernova explosions from those earliest stars. So the universe began with just deuterium and helium and very light elements, and those are what formed the earliest stars. And then when the stars exploded, they reached such high temperatures. If you want to know more about this, you can browse our past live casts into my Stellar Evolution live cast I did closer to the beginning of this series. But the heavier elements were created from the very hot, energetic supernova explosions of stars when they live out their lifetimes. And then we know that these heavy elements are within us. That's the saying, we are made of star stuff. Because the heavy elements that make up our planet and our world came from these supernova explosions. That's what they were created in. And it's actually believed that our solar system might have been spawned by a supernova explosion. So the supernova, the star nearby that would have gone supernova, would have seeded the collapse of our solar nebula, or the cloud of gas and dust that collapsed into the sun. When we look at this here, if we go forward closer to today, we have the dark energy and the accelerated expansion of the universe. That's something we're going to talk about more next week. But when we look at these sorts of diagrams, we're looking at a timeline, and we're drawing it in a way that indicates if we travel through space, we are traveling back in time. That's exactly correct. It's called the look-back time. So when we look at something very far away, since the speed of light is finite, it takes X amount of time for that light to travel to us. For example, the sunlight that we see, you're laying on the beach and you're getting a tan, those photons that hit you took about 8 minutes to get from the sun to our Earth, from the surface of the sun. Now they could have taken millions of years to get from the center of the sun, but that's a whole nother story. So it took about 8 minutes from the surface of the sun to travel through space to Earth, because light travels at a finite speed. So when we look at something even further away, say 4 light years away, the term light year is actually a distance measurement. So it is the distance that light can travel in 1 year. 1 light year is the amount of distance that light can travel in 1 year. So when we look at something that's 4 light years away, we are looking at something that took 4 years for light to travel to us. And 1 light year is about, if you use parsecs, is about 3¼ parsecs, or if you use miles, it's about 6 billion miles. So when we talk about something like the sun, we talk about light minutes because it's so close. It takes about 8 light minutes for the Earth to get to us, for the light from the sun to get to us. And when we look at something, like our nearest stellar neighbor or something, it takes X amount of light years for something to travel to us. And I misspoke. I might have said 6 billion miles. It's 6 trillion miles. I can't remember what I said now. But so when we are looking back through time at the most distant stars and galaxies, we are actually, when we're looking back through space at the most distant galaxies, we're actually looking back in time. The further away a galaxy is, the longer it took for its light to travel to us. And therefore, we are seeing it as it was that many years ago. So we're seeing the sun as it was 8 minutes ago. A star that's 4 light years away, we're seeing it as it was 4 years ago, and so on and so forth. So we call this concept, there's a mathematical term for it called the cosmological redshift. Now, don't confuse this redshift with the Doppler redshift, which is something I talked about several sessions ago in regards to a spectrum or a light curve of like a star, for example. The cosmological redshift, the concept of a redshifting wavelength is the same, but the cosmological redshift is due to an object moving away from us because of the expansion of the universe. So a Doppler redshift is caused when an object is just moving away from us due to anything. Orbit, for example. If a planet is orbiting its star, it's going to have a Doppler redshift when it's moving away from us around the star and a blue shift when it moves towards us. Cosmological redshift is when that entire galaxy is moving away from us because of the expansion of the universe. And so this is how astronomers talk about the time of the universe and how far away things are. The larger the redshift, the farther away something is, and the older something is. So let's look at this page here, which has a nice little graphic, if you can see this. So here it is starting. We have this galaxy is moving away from us. And you can see as it moves away, the wavelength stretches. It gets red shifted. It's turning red. Then we introduce another galaxy on the other side that starts to move away from us. And its wavelength is also red shifted. But if we assume these galaxies are of the same brightness, this galaxy on the right-hand side is moving away from us, but it hasn't been moving away from us for as long. And so it's red shifted less. So astronomers use this to determine how far away distant objects are because they know how bright they should be, and they measure their redshift, and they can determine how far away it is and how long it's been moving away from us, and therefore how old it is. So this is called cosmological redshift. Now this is a lot, and I totally don't fully understand this. There's a whole field, I'll tell you, there's a whole field of astronomy for each period of the universe's evolution. There are hundreds of astronomers, probably thousands, that study each of these individual periods because there's just so much to learn about them. And relating them to general relativity and trying to make all of that fundamental mathematics work out gets really complicated, and it breaks down at the moment of the Big Bang. So even though the Big Bang is the most well-accepted theory among the community for the start of our universe, not all astronomers accept it. We've explored a few other options last week, but namely there are two. There's the idea of eternal inflation, which kind of stems from the multiverse theory that the space-time is going to expand forever, but different parts of it expand at different rates, and some parts can stop and some don't, and so maybe there's multiverses that pop up. And then there's the oscillating universe, which says that there isn't just one Big Bang, but actually many of them, that our universe went from expanding to collapsing, to expanding to collapsing, and it may not always expand at the same rate, into the same size. Maybe you might have heard of this in terms of like a failed attempt, like how many times did our universe try to expand before it succeeded, for example. But the evidence for the Big Bang is considered overwhelming, I would say, by many. And it includes the expansion of the current universe, the cosmic microwave background, the abundance of helium, and the general homogeneity of the universe's matter distribution. When we look at something like this here, I'm zooming in, on the CMB, and we see that the distribution of matter in every direction is pretty much the same, that can be explained by the Big Bang theory. So while general relativity does break down at the moment of the Big Bang theory, the evidence for the Big Bang is pretty sufficient. Either way, there are roughly two options for the fate of our universe. If the universe is actually infinite in size, meaning it has no edges and it just goes on forever, it should also expand forever. If the universe is finite, however, it could eventually turn around and collapse back into the singularity that it came from. If you look at this, you see as the universe is expanding, things are getting further and further apart, which is slowing down. Well, I shouldn't say it's slowing down because it actually is accelerating the expansion, but it has slowed down considerably from the beginning. And even though it is accelerating, it could eventually stop accelerating and revert back and then collapse into itself in what we call the Big Crunch. One of the things that actually put a twist in this theory of the Big Crunch is the fact that the expansion is accelerating. And so I don't know where the state of that theory lies. I just know it's a possibility. Not in our lifetimes, don't you worry. But so next week we're going to talk about this dark matter and dark energy, and how does that play into what we talked about today, what we talked about last week with the CMB, the formation of galaxies, and the current evolution of galaxies too. There's a lot to talk about. Dark matter and dark energy, even though they share part of a name, they're actually very different things, and we don't know what either of them are. But we do know that they don't interact with light, which is why they're called dark. But we also know that they have to exist. Even though we don't know what they are, we know that they must exist because we've observed their gravitational effects. And we'll talk about this next week. So in other news, next week is going to be the last live cast in this Intro to Astro series. And I hope you're sad too, because I am sad that it's coming to an end. It's been so fun. And I do have exciting things planned, so don't fear. After next week, probably in about a week or two after that, I'm going to be developing curriculum for middle schools under this NSF grant. And I'm going to be testing out some of my middle school live casts for you all. So it's kind of Intro to Astro. It's kind of a little more, like a middle school level, but it's still the same concepts. We're just going to be teaching them in a curriculum-based way. And so I'm going to be testing those out on you all, and I'd really appreciate your feedback. So I hope that you stay tuned and follow along with me. And I'm also going to test out this idea of not having my live cast be the same time every week, but kind of jumping around, maybe hopping online last minute and be like, hey guys, in 10 minutes I'm going live on Slooh.com, sort of like Instagram story style. So I'm really excited for all this, and we'll see how it goes. In the meantime, before my live cast next week, of course, you can always check out Paul Cox's Practical Astronomy and Helen Avery's Constellation Stories. But on Saturday, we have an exciting show for you for the double blue moon. Now, you've probably heard the term blue moon a ton of times here at Slooh because we love it. We love talking about the blue moon. But what is a double blue moon? And I'm not going to give it away, but I'm going to tell you that you should chime in because it turns out, which we actually just realized a couple days ago, this is a rare event. We didn't even realize how rare it was. And so we're going to talk about this on Saturday, 4 p.m. Eastern Daylight Time, which is 2000. Is that how you say that? 2000 UTC. So I hope you'll join us then. I hope you enjoyed hearing about the Big Bang tonight. And I hope I taught you something, even though it's a lot and it's kind of confusing. I feel like I said that last week, but the more in-depth that these Intro to Astro series courses get, the more confusing I think I make myself sometimes. So just don't feel like you're alone because you're totally with me on this. So I'll see you Saturday and have a great few days. Clear skies, keep looking up.